Hello and welcome back to Differential Equations. We are starting chapter 5 today, and we are going to talk about linear algebra. We're going to have a crash course in linear algebra, which means that those of you who already know all of this stuff, you took linear algebra, you can relax a little bit. Those of you who did not, well, let's go over the basics. So this is a little crash course. Before I do this, just a quick, even though it's going to be in announcements in Canvas, if you did not send your work for the exam, if you're interested in those, in partial credit, right? Make sure you send me an email with pictures of your work so that I can attach it to your exams you guys took this weekend. All right, let's go and talk about linear algebra. So, linear algebra and differential equations are very closely together. We saw that we can solve systems using systems of differential equations. We saw that we can convert them to using that linear operator. We can convert them into just regular basic systems of equations. And linear algebra is very useful in the area of solving those linear systems. So we're going to take a look at matrices as the basic unit of linear algebra. Linear algebra is so much more than just matrices. We are going to take a look at some of the aspects of linear algebra and how it connects to differential equations. So not too much solving today, some basic ideas. And then starting the next class on Wednesday, we're going to talk about the eigenvalue method and so on. So let's first see what is a matrix. So I did say that matrix is a rectangular array of numbers. So matrix, hey, I clicked red. Matrix is a rectangular array of numbers. Rectangular array of numbers. Notation would be something like this. You can have A11, A12, A13, A21, A22, A23, and you can call that matrix. Right? It's a rectangular array of numbers. Now, this matrix would be 2 by 3, which means 2 rows by 3 columns. So now, if you want to, put any kind of a matrix, we are going to write. Now, note these brackets, which are, right, these are not straight lines like we're used to, because that denotes different thing, right? That denotes determinant. And we've seen that before. Now we are using brackets because we're just talking about matrix as a unit, as a concept in linear algebra. So we're going to have our A11, A12, A13, A14, ... So A1n. So this is all, if you take a look, they all start with A1 because it's a first row. And then you have second digit showing the column. So these are not 11, 12, 13. This is a 1, 1, a, and I'll show another notation very soon. Now, we're going to the next row, A21, A22, A23, A24, A2N. Going down to AM1, AM2, AM3, AM4, AMN. So this matrix is M by N, right? That's the size. M by N, meaning M rows, N columns. So you can have any number of rows, any number of columns. It's just important that it's rectangular. Square is okay as well. Square is a special rectangle, right? So square is a rectangle with all the signs same. So when you take a look at all of these values, right, you see that you can simply represent the whole matrix by a single notation, and you can just say Aij. I is a counter 1, 2, 3, 4, ... and I can go all the way to M. And then J is a counter 1, 2, 3, 4, ... all the way to N. So you can now pick any values. Say you pick a value A4, 1. This is 4th row, 1st column. I don't need to list the whole matrix. I can just pull 1. And these guys are called elements. Right? I can pull 1 element. So uppercase A. So maybe I should add that. Let's add it here. Notation. A, B, C. Those are matrices. And then A, B, C are elements or members, which are actually the numbers or functions. You'll see that. Well, you saw that in Wronski, right? Functions. So you can stuff in the matrix numbers, but then, guys, functions ultimately give you numbers, right? If you have f of x equal x squared, well, that's a function x squared, but then providing that x is 3, your x squared is 9, right? So it's a number. So what we do in mathematics, we upgrade, right? You have a number, then you have a function that will eventually give you numbers. Then you can have the integral of the function. You can plug whole integrals into this thing, and just go through the whole situation there. All right, perfect. So now we have this notation taken care of, and I'm going to give a couple of examples of matrices. 3, 4, 6, 81. 2, 2, negative 3, and 1, 0, 0, 1, and 6. So this is 3 by 4. Let's call A equals. B, let's make one very special matrix. This would be a square matrix, B. It's clearly 2 by 2. It's a square matrix as well. We can have 3 by 3 special matrix, which you will be working with a lot. Oops. So we are going to take this 3 by 3 square and so on. So these are just examples of matrices. Now, what do matrices have? They have numbers inside the matrix, and what we are supposed to do is have them, they represent not one but many numbers at the same time. And because those are just arrays of numbers, you know, 1 second. So let's go and see what we can do with numbers. We can add them, right? We can subtract them. We can multiply. And as linear algebra has it, we have no division. Woohoo, right? So let's talk about addition and constant multiplication and so on. So let's start with, I guess, properties, and all of these things could be blue. So constant multiplication, or multiplication by constant. I'll put C. So if you have C times A, that simply is the same as A times C because it's commutative, and all it means is C times I Aij. So the number would multiply every member of a matrix. So you will have 9, 18, 3, 12, 24, 27. So it multiplies every member of the matrix. If you have a constant in front, it multiplies every member of a matrix. So that should not be too difficult. The next property would be addition and subtraction of matrices. Addition and subtraction of matrices. So when we write the formula for this, we just have to be a little bit careful what it means, right, when you read the formula. So let's go and say that matrix A plus or minus matrix B is going to be Aij plus or minus Bij. That's the formula. Now this formula says something very important, which I'm going to write in blood. Matrices have to be the same size, same shape, same size. Everything has to be the same. They will have different numbers inside. Well, you can add this matrix to itself, right? So they will have their own numbers or the same numbers, but what absolutely has to be the same all the time is the size. So 2 by 2 matrix has to be added or subtracted from 2 by 2 matrix. We cannot have a different size. So I'll just put here in blood size of A and B must be the same. So something like that is actually implied from this notation, because A11, see, this I is 1 and J is 1, has to be added to the same I and J because it's the same letter in the formula. So anytime when this turns a certain set of numbers, like 3 and 5, then this is 3 and 5. So that assures that they're always the same. See, the value of the entry could be different because they are A and B. Right? Value of the entry, the element, the member, right, could be different. But the locations you are adding are always the same. So that's what it's encoded in the formula, that they have to be the same size. And then you just add or subtract corresponding locations, right, in the matrix. So if I have 17, 3, 2, and negative 9 as a 2 by 2 matrix, and I add another 2 by 2 matrix, let's say 3, 6, negative 1, and negative 7, whatever, then since I have a 2 by 2 matrix, 17 plus 3 would be 20, 3 plus 6 would be 9, 2 minus 1 would be 1, and minus 9 minus would be negative 16. There we go. So we started with a 2 by 2, we added 2 by 2, we got 2 by 2. Size remains the same. Now, probably you heard me at least once at some point in the class saying that in linear algebra you really don't have subtraction and division. And that's true. Subtraction is composite, right? So it's addition and multiplication. There are these big operations. And then subtraction and division are not. Even though division is the oldest of all, right? I mean, maybe addition would precede it, maybe. But division is the oldest, probably. I don't know. So what is A plus B, right? When you have A plus B, that is actually A plus negative 1 times B. And this is the reason why subtraction is not needed. This is the reason, right? You can also do the same thing with the division, but we don't use division here in linear algebra. You can divide matrices and so on, so we don't have to worry about that aspect of math. But there is your rule on what it means to subtract things. You are adding the inverse, the additive inverse. You are adding the additive inverse because B has its additive inverse as negative B. Those are additive inverses. So, oh my God, I put a plus here. It's a minus. Holy nightmare. Yes, thank you. I just seen this. I've just seen it. So subtraction is a subtraction, right? Yeah. All right, cool. So now we understand what A minus B means. And now we have some of the basic properties. Which are A plus 0 is equal to 0 plus A, which is equal to A. Now, I have to also write in blood over here, 0 is the 0 matrix of the same size. So I can have a 0 matrix, which is matrix of all zeros, right? For this one, it will be just 4 zeros in a pile, 0, 0, 0, 0, 0, right? That will be a 0 matrix. So it's one of the special ones, just like the one that has the ones, right, and so on. So those are special matrices. We'll get to them, but we need to know that the zero matrix of the same size is just filled with zeros. There is a, oh, by the way, and this one tells you that A minus A is 0, which is, again, zero matrix. So A minus A equal to 0. Those are the lower cases, and your numbers, right, are somewhat lowercase, I guess. And then you have a big, tall 0 that denotes a matrix, and the regular size 0 is a number, right? 0 number. So you can't be really sloppy when you're writing these things. You need to know what's... and the book uses bold 0 to denote the zero matrix, and it's using just a 0, right, for a regular number, the one that is printed on every page. So you have to be a little bit careful of the way you write. All right, cool. So that's that part. Now A plus B equals B plus A. That's the commutative rule. So it doesn't matter which matrix you add to which, right? It's going to be given. Then we have an associative rule. All of these matrices have to be the same size. Then we also have distribution, but this distribution can be done when you distribute C, or you are distributing A. Distributive rule, property, whatever, distributive property, whatever you want to call it. So these are some basic rules, and you have the option which way you want to add them. Again, all of the matrices per row have to be the same size. Now, C and D, lowercase c and d, those are constants, those are numbers. You know, positive, negative, whatever, non-zero, obviously, because that will make everything 0. You can create zero matrix by multiplying 0 times A. Note that my 0 is small 0 times A creates zero matrix. So these two zeros are not the same, right? This is the number, and this is the zero matrix. So be careful about that. All right. The next is another... I kind of did not freak out on any one of these. Well, transpose. Let's put it red. Okay, so transpose from the matrix is gonna go like this. If matrix A is given as matrix IJ, then A transpose, so you put this capital T like an exponent. So A transpose is going to be AJI. So you are in some sense flipping the entries inside symmetrically at 90-degree line. Let me give you two examples. We're going to do a rectangular, right, and then the special rectangular, which is square, right? So let's say that your matrix A is given as 3, 4, 6, and 10, right? Diagonal stays the same because Aij is the same as Abi. So the transpose would be 3 and 10 stay where they are, and 4 and 6 would swap their places because it's transpose, right? Now that's much better seen in the matrix, let's say B. This is the next example, matrix B. We'll come up with some kind of a longer, so let's go with -1, 6, 10, and -4, and then have 3, 2, 7, and 19, whatever, right? So what is the B transpose? Well, the B transpose now is going to be a matrix, right? This is 2 by 4. So this one is going to be 4 by 2. So your row becomes a column. You can actually write that as a row becomes column, and the column becomes row. So the row now becomes a column, so -1, 6, 10, and -4. And then we have the 3, 2, 7, and 19. So there is no calculation here. There is no, I mean, this is kind of formula, but all you do is you just write the values in different spots, right? Write the values in different spots, and that takes care of the transpose. There is nothing special going on about that. All right, so one thing that I will be mentioning a lot and using a lot as our terminology, we can write vectors as matrices, and we will call them row vectors and column vectors. So column vector would be a column, and they denote that with a lower letter bold, but we are going to use the arrow on top because we have to distinguish between now two different lowercase letters. Remember, the uppercase letter was a matrix, lowercase letter was the entry of the matrix or element of the matrix, but now we have another lowercase representing the whole row or column, and because those are row or column vectors, we are going to put a little arrow on top so we know what we are talking about. So column vector, and we can just say column vector B with arrow on top, and that's going to be some column vector like this, and we're gonna say, okay, that's gonna be B1, B2, blah blah blah, all the way down to BM, right? We can do that. Or, X vector is going to be X1, X2, X3, XM on the bottom. Then we have less used, but still used. We are going to use it. Row vector, right? And the row vector is going to be, so this one is M by 1, right? M by 1, and this will be 1 by N. Okay, good. For the row vector, we can use a C, and that's going to be C, C1, C2, C3, Cn. In terms of these ones, we do also have the X for it, but as I said, not used too much. We are going to use it though, but less used than column ones. Column ones we will be using, I'd say 95% of the times we use the column, and then sometimes we sneak in with this one. All right, so now I'm just going to do a quick notation summary. So we all know we are on the same page, because we are not using bold letters in our notes on exams and so on, right? We have to establish the notation. The book is very clear. You have entries that are not bold, and then you have capital and lowercase bold for matrices and vectors. We have to do the little bit notation here. So capital letters A, B, C are going, so capital, that's going to be matrices. Then you have lowercase, that is representing elements or members. And then we have these ones with arrows, column slash row vectors. Cool. So now we can take the matrix A, which is going to have, let's say, 3, 4, 6, 8, -1, 2, 9, 7, and 12, whatever. And completely dissect this into, let's say, vector C1, which would be 3, 8, and 9. Vector C2, which is 4, -1, 7. Vector C3, which is 6, 2, and 12. We're also going to have over here vector B1, that is going to give us 3, 4, 6. Vector B2, that will give us 8, -1, and 2. And vector B3, that will give us 9, 7, and 12. We can also pick any value if we want A2, 3, let's say. Well, it's going to be 7. It's the second row, third column. Second row, third column, right? So you can also pick any value you want. So now you see capital letter notation. You see the, ooh, I forgot my arrows. Holy nightmare. There we go. You are not paying attention. You did not all scream in chat that I forgot the arrows. So you see the capital letter to denote the matrix name. You see all of these guys, right, that denote the vectors. And then, you know, random, I don't know, random elements here. I did not list all of them. I just took these two, 823 and 823 and 832. Yeah. They denote the matrices. Cool. We are not nearly done. Next one. This is going to be a lot of concepts. They're all very simple. If you have never seen them before, you just sit and learn them all. They're all very simple. There's just a lot of them. A lot. Next one is the biggie. Matrix multiplication. So that's our next. And matrix multiplication is a little bit, it's interesting because you will be multiplying rows and columns and getting single entries that go into that location. Now, some of you have learned the dot product in Calculus 3, this is it, but you just have many of them. You don't have only multiplication of two vectors. You have a lot of row and a lot of column vectors. So you will have to multiply them all the same way, where the locations, corresponding locations multiply, and then you add them all up. And that creates one entry, and you just go from there. So this is going to be hopefully interesting. There is a formula that I'm going to say that matrix C, which is A times B, is simply the matrix of all of the AIs times BJ. So this is the formula which, there we go. So this is the formula which we are using to multiply the values, and what we are going to need here is certain rows and column needs to be the same for matrix multiplication. So you can't multiply anything, right? You have to have certain, you do have a certain restriction. So let's take a look at the matrix multiplication. The best obviously here is to work on an example to see the way this works. So I'm going to multiply, since you're multiplying rows into columns, right? Rows from the first matrix has to be equal. So let's put that as a restriction. Rows of A must be equal to number of rows. Okay. No. It's number of columns. Number of columns in the first has to be equal to the number of rows of the second. So number of columns of A has to be equal to the number of rows of B. So that's our restriction. All right, so let's go and say that you're going to have matrix A to be 3, 2, 8, and -1 times, let's say, it's maybe too big for, whatever. And then let's say you have 6, -3, 4, and another 6, whatever. There we go. Times, so that's A. Let's first define B. So now B can be any matrix, but it must have, right, since this is 4 by 2, right? So the number of columns is 2. We have to have 2 rows in here, right? Because it's going to go the row from the first onto the column on the second. So it has to have, this one has to have 2 rows. So what are we going to have here? Well, technically you can have anything. I'm going to go with A, B, C, D, and then A, B, C, D, and then X, Y, Z, W. All right, those are the matrices. And this one is, they don't have to be, okay, I'll do the next example to show that they don't have to be the same in terms of, or let me add another one. What should we add here? Let's add 6 for G and K. It doesn't really matter. It doesn't matter. A times B. Okay, so how does this work? Since this is 4 by 2 and this is 3 by 4, right? We can, right, we see that these are equal. So what do we do? We are going to take the this one over here and multiply by these and net them all up. So we have 3A. Oh, but this is going to be, because if I whatever. I hate this example. I hate this example because I'm not going to get a number to put here. I'm going to have a whole expression, and then it's going to be a whole expression for the next one and the next one. I don't want to mix numbers and letters because it's going to just be way too long, and it's not going to look nice to... So we're going with numbers here. 4, -2, 3 and 8, 11, 9, -5 and 6, and 1, -1, 2 and 3, whatever. All right. Now, you will quickly see that matrix multiplication is not commutative. I can't swap these because then the order wouldn't match and we would not be able to multiply. So what I'm going to take is the first column and put it on the first row. So when I multiply them, I will have 3 times 4 plus 2 times -2 plus 8 times 3 plus -1 times 8. If I want to color code these are multiplied together, green ones are multiplied together, purple ones are multiplied together, and the wood paneling or whatever this is, there we go. All right, so that's what's multiplied. And you compute all of that, and we use the first column in the first row, therefore it goes into 1, 1 location. So when I multiply all of this out, I get 12 minus 4 plus 24 minus 8. This is going to give me 20. This is going to give me 4. So I hope 24, right? 24? Yeah, 24. So the first entry is 24. Oh yes, this is that long. It's going to take a while, right? Oops. We still have this one. And then you are going to go to the next row. So first column and the next row. So that's 3 times 11 plus 2 times 9 plus 8 times negative 5 plus negative 1 times 3. No, times 6. So easy to make a mistake here. It's 33 plus 18 minus 40 minus 6. So these two will give me negative 7. These two will give me plus 12. So together is 5. Then we go here. 3 times 1. 2 times negative 1. 8 times 2. 8 times 2. And negative 1 times 3. That gives me 3. Minus 2 plus 16 minus 3. 3 and 3 will cancel, so 14. I don't have any more rows in B, so I am done. That's 24, 5, 14. Well, we're not done with multiplication because now we move 1 over. And reset there. 6 times 4. Negative 3 times negative 2. Four times 3. 6 times 8. It's just a little bit of calculation. So we have 24 plus 6 plus 12 plus 48. So the first one gives us 30, the second one gives us 60, so together 90. And now we write that first row, second column. Right? We do have a first row and we do have a second column. Now, we go to the next row here. Let's go green. 6 times 11. Negative 3 times 9. 4 times negative 5. And 6 times 6. That's 66 minus 27 minus 20 plus 36. So I have, that's minus 47, right? And then when you combine that with this one, you get negative 11. So altogether 55. I hope. And finally, what is the other color I haven't used yet? Orange. 6 times 1 plus -3 times -1 plus 4 times 2 plus 6 times 3 is 6 plus 3 plus 8 plus 18, right? So total should be 35, I hope. That's 26, 32, 35. 35. I got this back. It's supposed to be B times A. Sorry, B times A there. Okay, let's do another example so it's not backwards. Oh, by the way, B was 3 by 4, A was 4 by 2. You see how these are the same? Remember that was required? And look at the answer. Three rows, 2 columns. That always has to match. That always has to match. So the inner ones have to be the same. The outer ones gives you the size. Let's do another example, the better example. Say A is 1, -3, and 4, and then let's say it's 4, -1, and 0. And the B is 4, 1, 3, -2, 3, and 5, and 6, 7, 8, whatever. 6, 7, 8, there we go. So over here, I have 2 by 3, and over here I have 3 by 3. We see that I want A times B this time. Last time I messed it up. Okay, so here we go. So rows, 2 columns. So there we go. We are expecting 2 by 3 answer, right? But let's actually see it. So row onto column. I have 4 plus 6 is 10 plus 24, 34. 1 times 4 is 4. -3 times -2 is +6. 4 times 6 is 24. So together is 34. Good. Then I move 1 over. One times 1 is 1. -3 times this is -9. And 4 times 7, 28. That's 20. Move a 1 over. One times 3 is 3. Negative 3 times 5 is negative 15. 4 times 32. And that's going to give me 35, 25, 20. Another 20. Wow. Okay, fine. We're moving down to the next row. We are resetting the column 1 over here. So what do I have? 4 times 4 is 16. Negative 1 times negative 2 is positive 2. 0 times 6 is 0. So that looks like 18. Move the next column. 4 times 1 is 4. Negative 3, 0. So that's 1. And 0 times the whole row. I mean the whole column. And what is our answer? We started by 2 by 3, multiplied by 3 by 2, by 3 by 3, sorry. These are the ones that are inners, they're the same. So the answer has to be 2 by 3. There it is. Now, what is the stuff that you will be multiplying all the time in this course and the next course? Well, and this is something that I think, let me just skip ahead and see if this in this lecture, and because it should be. Oh, it's gonna take forever. Yep. So, how do you transform a system? 3x plus 2y plus 5z equals to 9. Negative x plus 3y minus 2z equals to 1. And then let's say you just have a y plus 6z equals to 4. You can represent this as matrices. This part can be a matrix A times the vector x equals vector of solutions B. These are column vectors. So what is your A? It's simply 3, 2, 5, negative 1, 3, negative 2, 0, 1, and 6. The column of your x, y, and z, and it's equal to 9, 1, and 4. There is a multiplication in here, obviously. So you can see that the row times the column is equal to the top number because you are in the first row. Just look at it. The x times 3 gives you 3x. 2 times y gives you 2y. 5 times z gives you 5z. And then you have your 9. And then when you have the blue one, that's negative 1 times x, 3 times y, negative 2 times z equals to 1. And orange, purple, 0 times z is 0, right? You have 1 times y, 6 times z, and then you have your 4. It's very systematic. So we will be using this a lot, this notation. Let's do one more matrix multiplication and then move to some, maybe let me just go get something from homework. You know, one from homework. Okay, so this one says multiply and show that they are not. Okay, so multiply both ways. Okay, it's problem number 3. You'll have many more of these in MyMathLab. So 2 and 3, 0 and -4, -1 and 5, and B is 1, -7, 3, 3, 0, -2. They want AB and they want BA, and then we can write something in capitals. All right, cool. So 2, 0, -1, 3, -4, 5 times 1, -7, 3, 3, 0, -2. The row onto the column. So if I'm starting with 2 by 3 and multiplying by 3 by 2, I'm getting 2 by 2 answer. So 2 times 1 is 2, plus 0, minus 3, it's a -1 on the first entry. Then I move to the next column. 2 times 3 is 6, 0 times 0 is 0, -1, so plus 2, that's 8. Then I move to the next row and the column over here. So that's 3 times 1 is 3, negative is plus 28, plus 15. That's 18, 28, 46. And then we move there. 3 times 3 is 9, plus 0, minus 10, that's -1. All right, cool. So that's what we have for A times B. Now we want to do B times A. That's going to be 1 -7, 3, 3, 0, -2, times 2, 0, -1, 3, -4, 5. So this is 3 by 2, this is 2 by 3, and what are we expecting over here? 3 by 3. Well, that's not going to be the same as this, right? Because even the size doesn't match. We don't even have to compute values. We see they're not going to be the same. So the big takeaway is this. Matrix multiplication is not commutative. Right? What's commutative is when you multiply it with a constant. So matrix times a constant is commutative, but matrix multiplication is not commutative. So can you find examples? Yes, you can find examples, but in general it's not going to be. All right, so I have a row onto a column. So that's 2 plus 9 gives us 11. Then move 1 over. That gives us -12. Then move 1 over. That's -1 plus 15 gives us 14. So that was the first row into all 3 columns. Then we move to the next row. Reset the columns. So -14. The next one is 0, right? Because -7 times 0, and then 0 times -4. That's cool. And then the last one is 7 minus 10, negative 3. Right? Yeah. Now, move the column in a row. Six minus 6 is 0. Move the column. 0 plus 8 is 8. Move the column. Negative 3, negative 10, and negative 13. Done. They are not the same. They're not the same size. They don't have the same members, right? It's just they're not the same. Therefore, right? Done. So that's matrix multiplication. And there are some rules that do hold. Properties that work are A, B times C is equal to AB times C, so that holds, and A, B plus C is equal to AB plus AC, so these hold. But commutative rule does not hold, so be very careful there. I mean, even if you go to my previous example here, right, it works A times B, B times A you can't even do, right? Because it will be 3 by 3 times 2 by 3, and these are different. So it cannot even be done, right? If you flip it. Okay, the next big concept that we also need to define is going to be what is called identity matrix. Now this one gets read. This one is a big deal. You'll be sick of this one. It's 1 and then all zeros. And then 0, 1. And then all zeros. 0, 0, 1. All zeros. And then if you go down, it's all zeros, ends with 1. So identity matrix has following properties. Always a square. It's always a square matrix. Then all zeros except the main diagonal, which is all ones. So all zeros except the main diagonal, which are all ones. So if you remember that, you can create any identity matrix you want. It looks like I made some computational errors somewhere. A23, A31, A33, I added wrong maybe, I don't know. Now I'm interrupting this very important concept to go back and check arithmetic. A31. So this one and this one. That's 6 minus 6 is 0. A31. 6 minus 6. And then A33, that's negative 3 and negative 10 is negative 13. Yeah, it's good. It's all good. All right, so identity matrix is a square matrix that has all zeros except the main diagonal. So when you want the 3 by 3 identity matrix, you would have it as, and this is the one that we use most of the time, 1 0 0 0 1 0 0 0 1. So that will be identity matrix. Some of the properties that we need. Well, let's write it. A times I is the same as I times A. Equals to A. So if you are multiplying by identity matrix, it's commutative. That's the. You remember how I said, yeah, we're gonna have shiny exceptions. Well, this is one of the exceptions. So, in general, multiplication is not commutative, but if you have identity involved, it's always a square, and you're just multiplying by once. In this case, it turns to be commutative. And this one needs to be square. I forgot to mention that. So let's say square as well. And one thing that we did not define yet, and that's what we are going to need, is the inverse of a matrix. And that is going to be matrix A to the minus 1. So now we'll deal with that how we get it. Don't panic there, right? We'll just need to write that A times A inverse is the same as A inverse times A. It's going to be I. So it is a little bit tricky on how to get these matrices to work, to get the matrices, because first we have to also this determinant, and then we can define the inverse of a matrix. So there's a whole bunch of things that we have to first deal with, and then we're going to. So inverse of the matrix is just denoted this way, so I can write the property. Now I'm going to say determinant of matrix A is denoted as absolute value of A, and we know what that means when you solve 2 by 2, 3 by 3, 4 by 4 cases, because we have seen them throughout mathematics already. Remember that thing? So determinant of matrix when it's 2 by 2 is AD minus CB or BC, whatever. For 3 by 3, age, and I don't want to confuse the letter with the counters, so let's use I don't want to use I, J, K, M, and N. Let's use letter P. So this one was A, and then we have EP minus age F minus B, and then I have DP, right? DP minus GF, and then plus C, DH minus GE. All right, so that was a 3 by 3, and so on. So this is my determinant, and you have seen this in Wronskian. Those of you who take Calc 3, you've seen this in a cross multiplication and a whole bunch of other areas. AIX plus I'm not sure. I'm not sure what this is in chat. AI plus IA, and then I'm not sure what that means. These formulas, if you're referring to these two formulas, they're good. I'm not sure. Yeah. You can type again, and I'll go back. All right, so determinant, and the reason why we need determinant is so we can get the inverse, right? So now I can go back to inverse. Back to inverse for 2 by 2. We're going to say if A is equal to, well, now red again. If A is equal to A, B, C, D, then A inverse is 1 over determinant of A times D negative B negative C and A. Oh, how to find, yeah, well, that's what we're working on right now. So here is the formula. As soon as your question came in, right, I am boxing the formula for the inverse of a matrix. So, and being that, most of these systems will reduce down to 2 by 2, I mean, this can be extended, obviously, but it's just a lot of calculations. Let's work out on a matrix. Say A is 3, 4, 8, and negative 2, whatever. What is the inverse? Well, clearly we need the determinant first. So we find the determinant by negative 6 minus 8 times 4 is 32. So altogether negative 38. And now the inverse is negative 1 over 38 times the matrix. You swap the diagonal, so negative 2 and 3, and then you put the negatives on 8 and the 4. And now you multiply the constant in front into each one of the terms. So it becomes 2 over 38. It becomes 4 over 38. It becomes 8 over 38. And it becomes negative 3 over 38. And that's the inverse. Now let's say you want to check. All you need to do is to multiply these two. Need to get I2. I2 is 100010. Because we had this rule right here, which says that no matter which order you multiply them in, it will always give you identity matrix of the same size. So, if you are to multiply A times A inverse, so A was 3, 4, 8, negative 2, and you multiply that into the inverse matrix, and I'm not going, I know I can, well, you should reduce, right, for inverse, so 1 over 19, 2 over 19, 4 over 19, and negative 3 over 38, right? You should be reducing that. But since I will be now multiplying to check, and I will be, working on all of the, common denominators, then it's easier for me if it's not reduced. But as the answer in my MATLAB, you better put reduced numbers, otherwise you will be computing it from scratch, right? So I'll put the reduced answer actually here. So 1 over 19, 2 over 19, 4 over 19, and negative 3 over 38. That one can't reduce. All right. So now what do I have here when I do the checking? I have the row onto a column. So that gives me 3 times 2 is 6. 4 times 8 is 32. Gives me 38 over 38, and that's 1. Then the next entry, 4 times 3 is 12. 4 times 3 is negative 12. So that gives a 0 over 38 over here. Then we move to the next row and column. 8 times 2 is 16. Negative 2 times 8 is negative 16. So that gives us 0 again. And finally, 4 times 8 is 32. Negative 2 times negative 3. Well, it's wrong. Oh no, it's plus 6. I need 38. That's 38 over 38. Good. So 1001. Oh, it's good. Yeah, 4 times 8 is 32, and then yeah, I didn't see the negatives there, so my brain went full-blown panic. But it's good. It worked. All right. So we know now the way to compute the inverse of a matrix. Now, is this it? No. Take linear algebra. You are going to find inverses, right? There will be full lectures on inverses. They're not going to show up just like a little, oh, by the way, right? They're going to have a full section and a whole bunch of rules related to inverses. That's why you take that course. Over here, we just skim through all these concepts that we will need to some extent. The next is the matrix valued functions. And this is where the fun begins, because now we understand, and I already hinted this earlier, we get to plug in the whole functions into matrices, and this is where we begin our use for differential equations, because up to now we only placed numbers in equations, and that's not what is interesting for differential equations, because differential equations are equations which contain functions, right? Regular equations are ones that deal with numbers. So what we have done so far is useful for pre-differential equations, right? But for differential equations, since your main focus is to find x of t or y of t or y of x, depending on what your MyMathLab is asking for, we need matrix valued functions, which means that our matrices now will contain functions. So say a of t is going to have a function of t, another function of t, another function of t, all the way until we reach the 1n of t. And that's going to do the same thing, 1. So now we are going into the second row, first column. It's a matrix, right? And each one of these is going to be a function. And when you get to the last over here, it's going to be m1 of t, am2 of t, am3 of t, and then finally mn of t. They can be rectangular, special case. They can be squared, right? They can, do all of those things, but now they are functions, right? So you can literally have, as an example, you can literally have something like this. X squared cosine x e to the, let's say, 2x and sine hyperbolic x, just to make it as colorful as possible. All right, there you go. So now you have all of these right together. The derivative of the matrix is the derivative of every entry of the matrix. So you take every individual function and you differentiate. So looking at my example up there, a prime of t, so this is a formula which says differentiate every entry. So it will be simply 2x, 2e to the 2x, negative sine x, and cosine hyperbolic x. So there are no product rule, quotient rule, and so on, right? This is just each entry is a function on its own. Each entry gets its own derivative, right? There are no special rules to deal with. And that allows us to introduce derivatives into functions which are in matrices, which allows us to start writing the systems from before as matrices, so that we can reduce them eventually into matrices and use matrices to solve systems that have a lot of rows and, a lot of different unknown functions. So first order linear systems. The first order, right? So that means we are only looking at first derivative. First order, first derivative, second order, second derivative, and so on. So for the first order, we're going to have, and I'm going to use, let me just see, the same notation like they use in the book. I believe they use P. Yes, they use P. All right, so x1 prime is p11 of t times the function x1 plus p12, some function, right? x2 plus ... ending up with p1n of t xn plus f1 of t. So we have x2 prime. This is the second differential equation. Now, before I start writing this, right, these are your different solutions. Functions like x of t, y of t, z of t, but because we are going to have, whatever amount of them, it's better if we just call them x1, x2, x3, right? So those are the solutions that we used to call just x and a y of t. Now they're x1, x2, x3, x4, because, with these linear systems, you can just have a 100 by 100 or 100 by 7, whatever, right? You can create the system of whatever amount of variables. Now, obviously, for classroom and exams and so on, the homework, right, we are not going to have 100 unknown functions, right? So that's why we can use x of t and y of t, and then when we want to be extra annoying, we say z of t as well, and then you have 3 of them, right? But in practice, the weather forecasting system is a system of 23 coupled partial differential equations. All right, 23. So there are 23 different functions that have to be, right? And then you have a whole bunch of initial conditions for the weather model to work. You're talking about current temperature, current pressure, current humidity, current, right? All of the little, things, little things, right? All of the important aspects of weather are calculated by those models that are continuously, right, work and take the current input to compute and predict what is going to happen with the weather in the future. Those are differential equations, right? And having 23 of them, this is the information that it's, right now, 13 years. I think I heard that one 13 or 14 years ago. That's probably improved and better. Maybe they have now 25 equations. Maybe they reduced it down to 18. Just whatever numbers out there. But the one weather model that I heard at the mathematical seminar had 23 equations that continuously worked on the current input to produce the weather forecast for a given, right, region. And again, right, depending on how good the input is. So, when you have 23, functions, that's x1 through x23, right? And then you need all other variables as well. So it gets a little bit annoying to have different letters. So that's why we use x1, x2, x3, and so on. I hope that now makes sense. So now we're going back and we say x1 is equal to all of that mess. X2 prime is equal to, now it's going to be p21 of t x1 p22 of t x2 plus the p2n of t xn plus f of 2. My f2 of t could be any function. So this is for, right, remember homogeneous and non-homogeneous? That's where it goes, either a 0 or a driving term. All the way down to x prime n, which is p n 1 of t x1 plus p n 2 of t x2 plus the plus p n of t. And before you scream, where is my m? These are all square matrices. You have to have the same amount of matrices as unknown functions. That should be something that, right, you know from basic systems. Your number of variables, in this case unknown functions, has to match number of equations that you have. So you know that the second order system gives you 2 answers, third order system gives you 3 answers, right? If some of them are complex, well, they're just going to give you sine and cosine, so those are 2 separate functions already, right? So the number of equations equals the number of unknown, I'll write that. Number of equations equals to number of unknown functions. In our case, xn. So that has to match. So now, if you put all of this mess together, you can create a couple of matrices. You create the capital matrix P of t. You create a column vector, which is the good old x1, x2, all the way down to xn. And you also create f of t, which is the driving, right? f1 of t, f2 of t, fn of t. So it creates all of those. And now, finally, in blood, we get to write dx over dt is equal to ptx plus f of t. That, oops, forgot the arrow there, sorry. That, forget the arrow here. Oh, nightmare. It's a column vector. This over here is your linear equation first order, except it's a system. So if you are to go back and look at our linear systems from the class number 2, I think, right? When we started in January, I would say class number 2, maybe class number 3, but it should be in class number 2. You are going to see the dy dx is equal to p y plus f of x. Right? You're going to find that equation. That is in there. If you only have x1, then it will look like this. dx1 over dt will be p of t, which is a function, right? P of t times x1 plus f of t. Right? If you only had index 1. Well, that's the same. So what you learned for the linear systems from before is still in this red equation, but you only have your order to go up to, not order, sorry, the number of functions, well, yeah, the order, to go up to 1. So you don't have x2, x3, so you don't have other equations. You can have other equations added, right? And then you are creating a larger system. So I hope you understand that this equation includes your chapter 1 in it, right? And the cool thing here, right, is that, well, first let's write this. So if f of t is equal to 0 vector, right, that's the big 0, then we have homogeneous system. Then differential system is homogeneous. I don't know why, but I always keep dropping that E. I probably, if you go back through my lectures, you'll find it missing area. I don't catch myself every time, but it's annoying. I tend to drop it. Right. So if that is the system you have, right, then it looks like dx dt is equal to p of t x, like that. Now, do we all agree that this over here is your vector of solutions? Right? The x bar is the vector of solutions. It's x1, x2, x3, all the way to xn. Those are all functions of t. I'm cluttering it now, but it should be understood because we are not dealing with numbers now, we're dealing with functions. And for 2 by 2, right, if we multiply by the inverse of p, we will get it alone. Right? Now, I'm trying to see if they put that in this lecture or they move that somewhere else. Nah, that's somewhere else. I'll just put this as a note. To solve, get P inverse and pre-multiply both sides. Now I had to use the word pre. I hate the word pre, okay? When they say pre and then something, because like preheat the oven. What do you mean preheat the oven? Just heat the oven, right, to 400 degrees. It makes no sense to post-heat the oven. That doesn't even exist as a concept, so it's stupid to say preheat in a first, right? If you just think about it for like 7 seconds, right? But I have to say pre-multiply because P inverse times P is not the same as P inverse, right, post, because depends on what you have in multiplication, right? You have to pre-multiply here because there is the column vector involved as well. So you would put P inverse there and a P inverse there. Then these will cancel, leaving X to be just a matrix of these. So we'll deal with these things later, I just went in the book to just make sure what else they have so I don't go over, because we literally have 7 minutes left. We've been at it at 2 hours straight, and it's still not done. So let's see what else is there. So now the solution, right, is going to be x of t is c1 x1 of t plus c2 x2 of t plus dot 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 cn xn of t. So that's our solution. And we'll have to see all of this obviously in an example. So one of the examples, I'm going to steal the example from the book in interest of time, because we don't have time to solve this. We'll have to probably continue this on Wednesday. We have 4, 6, -3, and -7 times x bar, like that. And we are supposed to solve this mess, right? The solution works out to be C1 3e to the 2t 2e to the 2t plus C2 e to the -5t 3e to the -5t, like that. So that's one of our possible solutions. Oh no, one of the possibles. That's the solution. Right? That's the solution. And you can write this one, because this thing is x1 x2 vector. Right? You can write this as x1 is equal to 3c1e to the 2t plus c2e to the -5t, and x2 equals 2c1e to the 2t plus 3c2e to the -5t. So the way this works, and what we are doing now is we are just representing the solution. You have your system, which you convert into a matrix. You solve the matrix, you will get this. And once you have that line, you can write it in the way that you used to from previous chapters. Like in chapter 4, you wrote these two separately. Okay, so now how does this work? Well, you are starting with a system 4x1 minus 3x2 equals x1 prime, and 6x1 minus 7x2 equals x2 prime. So this is where you started. If you don't like x1 and x2, go ahead, use x and y, right? They're all in terms of t. I'll just put here in a parenthesis note, x1 is old x, x2 is old y. If you are confused by these things, it's just x1 and x2, and then if you have a third equation for a z, we'll just go x3. it's, just making sure that we can do this past 26 letters in alphabet. Now, this could have been given to you in any shape or form, but this is the one, and from here we are able to extract the vector of primes, which is dx dt, is equal to the matrix of coefficients and then the matrix of solutions. Actually, let's do step by step. So let's write this one as x1 prime, x2 prime. So now this is my derivatives are equal to 4, -3, 6, -7 times x as a variable, and that's how we get this line. So you are going to see the system given, and your job is to create the matrix here, right? And then solving that matrix, right, we're going to see what is the way to solve the matrix later on, right? We can deal with we will deal with that in later sections, and that gives us the value. Independence of solutions, that's still the Wronskian, right? So we have to So Wronskian is still what we use to figure out the independence. Yeah, x1n. Just writing the same matrix all the time. Right, so we take the determinant and we make sure, right, it's a non-zero. For independent. So we still have a little bit more to cover, and I will have to continue this lecture. So next class we are going to finish 5.1, and we have to do a lot of examples. This is, a lot of linear algebra covered in one lecture, and then trying to make connections to differential equations and the way they connect. So there will be a part 2 of this on Wednesday, and we are actually going to solve some of these things so you can see it now. So try to practice the basics. I'll open the homework. Try to practice the basics for this for these calculations for linear algebra. You don't have to worry about differential equations yet, because I will be covering that on Wednesday. Sorry, I have to just cut this short and leave, because I have to go to my other class, which started 3 minutes ago. Bye.